Today's lecture 23. You will learn about electromagnetic waves. First, any question about the class? So this is the rough plan for the next 6 weeks or so. Our next exam will be on April 1st, because typically if I set it on Fridays, somehow organic chemistry instructors love to have exams on Friday, so that's the reason. Exam 3 will be from lecture 17 to lecture 23. It's frozen. What else? Maybe we can talk a little bit about exam 3. I uploaded a study guide. It's here. And then, but I may add more questions. Can we, sorry. Do you have any question? No, okay, good. So that is a study guide. There is no answer for study guide 3. But I will put answer probably a day before the second review session, like last time. Any other questions? I sent your grades yesterday. If you don't receive any email from me, please email me. What else? I received many requests for extra credits. Is it common thing in other classes? So I just talked to the other instructor who has been teaching this class far longer than me. So I will copy his policy. So there will be very small, well, copying his words, he said it's too much. It's basically you can add 2 points to your exam. That's, for him it's too much, but what do I know? He has been teaching this class for so long. Basically, it will be a list of questionnaire, like how many hours did you prepare for exam 2, what you did differently. So I can also benefit from that survey. Okay, it will be up sometimes next week, as soon as I receive his the survey from him. Any other question? If not, let's start. So anyone still remember what a wave is? Last time we talked about wave. What is the definition of a wave? And yes, yeah, Natalie. Yeah, if you download that thing, so right now to download this document, unfortunately, it's a window capture, but there should be a equation sheet in that document. So what is the definition of wave? Any guess? Nick. That's your name, right, Nick? What is your last name? I cannot pronounce your last name. Bekowski? Okay. What is the definition of wave? What is a wave? Like this? Okay. Wave is like this. Wave is propagation of disturbance in space. Okay, and there are 2 types of waves. We will just do a quick recap here. One is longitudinal, meaning the disturbance is along the direction of the propagation. Like when I talk, I disturb air, and it propagates, it hits your eardrum. What is the second one? Yeah, what is your name? Transverse, okay, for standing wave. So for standing wave, the disturbance is perpendicular from the direction of the propagation. And wave doesn't have to be mechanical. Of course, you have seen ocean waves, which is beautiful, but in this lecture, we will talk about electromagnetic waves. And in last lecture, we discussed that Maxwell calculated that electromagnetic wave, it looks like this. That's let's say the electric field and the magnetic field in blue. So this is I don't know, Y. Z. So the magnetic field can look like this. And Maxwell calculated from first principle. He basically derived a set of formula using Ampere's law, Faraday's law, Gauss's law of electrostatic and magnetism. That the speed of light, which is c, is equal to double E, is equal to 1 over square root of epsilon naught and u naught. And these two are fundamental constant of nature. So this is quite amazing because basically you can measure epsilon naught from, let's say, a capacitor and mu naught from, I don't know, an inductor, and somehow you get speed of light for free. So we did that last time. What else? And then one thing that I didn't mention is that if this is E, which is electric fields. So the electric field varies as a function of time and distance. And B is in red. B is smaller than E by a factor of also C. So that's this one's new information. There are some simulation that you can play. Here is one of them. So the link is on Keynote, I think, on the presentation. So the electric field propagate, let's say, along, it doesn't give a label, along vertical axis or green plane. Okay. Like that. And then the magnetic field propagates along a plane that is perpendicular with respect to the green plane. And the magnetic field looks like that. And this is basically what I'm trying to draw. So the propagation is both electric and magnetic. So I don't know if you still remember, like B, maybe not. This is part of exam 3, not the electromagnetic waves is part of exam 3, but this one is also part of exam 3. The name is Ampere's law. And then this is Faraday's law. The EMF is basically equal to flux, magnetic flux property. Basically, if we put a line here, I'm just going to sketch what Maxwell did because it typically takes me an hour and a half to explain his derivation to physics students. Let's say if we put a closed line here, so this delta L, then since delta B or the magnetic field changes, therefore there is electric field. Okay. And similarly, E, there is another term which is a function of E here. The name is displacement current. Since E changes, then there is B. So basically, the energy slosh back and forth between electric fields and magnetic fields. And a brief recap. Energy per unit volume, which is energy per unit volume. This is from, I don't remember what lecture, probably lecture 10. Is 1/2 and the energy per unit volume of a magnetic field is 1/2, and then there is U naught here times p squared. Another thing that is beautiful about this type of derivation is that it doesn't matter where or how the fields are generated. So we derive the first equation from when we study capacitor. The second one is when we study inductor, and the equation is still valid, even when we study, let's say, a black hole or radiation from the sun. So we will use all of these equations today. But let's look at the propagation of one of the fields, which is electric field. So if you look at these fluctuations, it's periodic, which is nice, and it reminds you of what function? Sine function. Okay, so in fact, when I teach this class, maybe when Maxwell did it, he guessed the solution. He used sine function. So, and this is a typical solution for a standing wave, for a wave. For this class, let's use that term. And we know that E is a function of distance and time. What I mean by that, if I stop time, the intensity of the electric field depends on the distance, right? But if I fix x, if I fix the coordinate, let's say I just focus on x is equal to 0, it changes over time. This is why E is a function of x and a function of time. And typically, we use E max or E naught. I think I use E max. E naught, sorry. So this is just the amplitude times sine times kx minus omega t. Okay. Has anyone seen this equation before? Did you study waves in physics 111? No? Okay. So k is what we call wave number. And omega is, I think, angular speed. Sorry, you should let me know. Okay. Actually, correct. My Zoom is frozen here. And then this one is equal to 2 pi times divided by lambda. And then this one is equal to 2 pi divided by period. Okay. And lambda here, what is lambda? You still remember from your perusal? This is the wavelength. Good. And I will define or describe what a wavelength is. And then what is capital T? This is from 111. Capital T, or 1/frequency, is the period. Okay. The unit of wavelength is meter, and the unit of a period is what is the unit of period? Huh? 1/Hertz, which is equal to the unit is time or second. Okay, so in some book, I think this is how your textbook write it. They use 2 pi x divided by lambda minus t divided by. So here they just collapse. They just take 2 pi out of the expression inside the brackets, and then they can write the expression this way. Maybe that thing is easier for you. So basically, x will vary, from -infinity to infinity, but this is the ratio of x with the wavelength, and this is the fraction of time with respect to the period. Okay. Let's see if this simulation helps. So this is a cross section of, this is a different simulation also from this website, GeoGebra. So so we can, it's a basically a standing wave. It's a sine that moves with respect to time and distance, meaning if I fix time, depending on where you are, the intensity of the field changes. And then if you, let's say, only care about one coordinate, if you let time runs, the intensity also changes. Any question? Ashley, do you have questions? Good. So this is a little bit, it took me a while when I was I learned this when I was a high school student. It took me a while to appreciate it. So if you can pay attention, it will be better. I mean, you already pay the tuition. Might as well get something out of it. Thank you. All right, so this simulation. So I have this iClicker question for you. Okay. So it's a reading quiz, basically. So the question is, in a sinusoidal traveling electromagnetic wave in a vacuum, the magnetic energy density is basically, just as a hint, magnetic energy density as given above is proportional to B squared. So basically, another way to express the question is the magnetic fields is either A, B, C, D, or E. Time to read the question. Very good. So more than half of you have answered. 10 more seconds. 5, 3, 2, 1. Okay. So that's so the answer is B. So let's go over it together. So the option A is the same at all points. No, it fluctuates like what we see here. And then second is maximum when the electric field has its greatest value. That's correct. It's maximum when the electric field is 0. It should be minimum when the electric field is 0. And then the rest is negative when the electric density is positive. What is wrong with option D? Or you guys stop reading when you find one correct answer? So the energy density, which is energy per unit volume, is proportional to B squared. Okay, and when you square a number, you cannot get negative values. Some of you may answer E, but not many of you. Excellent. So what? 80% of you got it right. Any question? Next is by using this equation, you can also show that the speed of light is equal to C is equal to lambda times F. Okay. And lambda is 2 pi divided by K, and F is, sorry, 2 pi. F is equal to omega divided by 2 pi. So put these two expression, substitute these two expression for lambda and F. We get 2 pi divided by K, omega divided by 2 pi. And then, so C is equal to omega divided by K. And then on the lecture notes, I think somehow I choose to write omega is equal to K times C. So this is the equation in your lecture notes. I think we're running way behind, so I'm not going. I'm gonna put this lecture notes with the answers after the class. You can do the iClicker yourself. One thing that I want to make sure is that before we continue, I want you to be familiar with what 2 pi is. You know what pi is, right? 3.14 or 20. Do you do this here in the US? Pi is, or no? Or this is only in, okay, so but I think the older you are, people use 3.14. So basically, for this type of calculation, we use a different unit of angle. Have you seen this or no? Which is radian. So this is a degree. This is radian. Okay. So for 0 degree, the small circle is degree is equal to 0 radian. This is like absolute angle. So you don't need to put 0. You don't need to put degree here. How about 360? 360 degree is equal to, in radian, 2 pi. So probably some of you haven't seen this. Okay, good. I'm glad that we are taking time to do it. So this is the unit that you use for this type of calculation. And then when you do on the exam, make sure you know how to use your calculator. Either you use degree or radian. If your calculator insists you must use degree, when you see 2 pi, you put either 0 or 360, well, 360 degree. And then obviously 90 degree is equal to pi divided by 2. This is, it goes without saying. Right? Dot, dot, dot. Any question? So next, a wave propagates, and we define the direction of propagation by using right-hand rule. This is the last right-hand rule that you need in this class. So the direction of the propagation. First, I have to introduce intensity, which is at the end of this lecture. But this is just my way to show, I guess, teach you the direction. So S, anyone still remember from Russell? What is S? S is a vector. What is S? Arban. What is S? S is it actually says right there. It's pointing vector. It points towards the direction of the propagation. It took me decades to realize that pointing vector is named after John Poynting. Because yeah, I barely speak English when I was a high school student. I thought that, oh, it's pointing towards the direction of the vector. This person is actually real, and he is a first-class scientist. So it's a vector. E and B actually are vectors. There is a name for it in more advanced class, which is curl. basically the direction here, I don't know how to say, let's just write R. Okay. So here is the direction of, so R is the direction of propagation. We will do iClicker for this. So I want to make sure that you guys can answer it today and on the exam. So there are two ways of figuring out the direction. Let me show. Your textbooks prefer a line, you know, like place your hand along the direction of the electric field E, and then let's say B like this. Then the right hand rule, you curl your hand from E to B, not the opposite, E to B, and this is the direction of the propagation. Called S. Let me change it to small s. Looks a little bit nicer. So this small s can be x, y, z plus x minus x minus z. I don't think I need to know this, but or a combination of any of these factors. Basically, it points towards certain direction. So that's one way. Another way is you can just use your hand like this, E, B, and S. Your thumb is the direction of the propagation. Good. Any question? So your middle finger is always B, and the thumb is always the thing that you want to calculate traditionally. In this case, the direction. And then the other one is the other one, just in this case, the electric field. Okay. So I have this iClicker question for you. It looks a little bit messy, but I will give you a hint. So let's show the iClicker. So at a certain point in space, so the reason why it doesn't have sign, period, and frequency like in this expression, it's because we fix certain time and space. Okay? Certain point in space. There is no time there. There should be time. The electric and magnetic field of an electromagnetic wave at a certain instance are given by something along x-axis and something along z-axis. For this problem, all you care is the direction of the fields, which is x and plus y, because I can put negative signs there if I want to. The wave is propagating in the positive x, negative x, plus y, negative y, or unknown direction. Any question before we start? Let me, so one thing, sorry, can I get your attention a little bit? So another thing in science, in any fields, and don't underestimate the number of people that don't know how to do this, by the way. This is the convention for the direction of z. Basically, it also follows right-hand rule. We curl from x, y, and this is the direction of z. Or something like okay. So basically, all of you have answered. 5 more seconds. 3, 2, 1. All right, so that's the results. 60% of you answered D. So let's do this together. So first, be careful with the. It took me a long time to figure out that I gave you B instead of S. So make sure you know which one is E, which one is B, and what is being S. Sometimes, because I wrote this question a long time ago, I thought that I knew what I wrote. So E and B, right? So E is along x-axis. Let's use this convention, x-axis. And then B is along z-axis, positive z-axis. So S is along negative y-axis. So the answer is D. Okay. So more than half of you got it right. Any question? I think this is the last right-hand rules for this class. And this one you can, I know you, from, if you learn from previous problem, then you should be able to do this problem. Next, we will talk about energy density. And energy density is simply the energy per unit volume, and it's given by this formula here, and also shown on the right screen. And if you like math, you can combine these two. Okay, first, one thing that you should know is that the magnetic field is smaller than the electric fields. So we often just think of electromagnetic wave, at least when we do problems in the context of electric fields. But since you know that E is a function of, B is a function of E, sorry, B is a function of E, then the sum of the energy, so sum of energy is equal to UE plus UB. Right? Can you see this? It's equal to 1/2 epsilon naught E squared plus 1/2 mu naught B squared. And this one is equal to 1/2 mu naught times. What is B again? What is the strength of magnetic field? The strength of the electric field divided by C. Is that correct? Somebody, because I will be sleepy in the next 2 weeks or 3 weeks. I'm really sleepy. I've been, yeah, I sleep for, I don't know, 4 hours daily in the past few days. Thanks to my son. So, and then what is C squared? C squared is, C squared is this one, right? So C squared is 1/mu naught times epsilon naught. So C squared, so this one is equal to square mu naught times epsilon naught. So this one cancel. So this one is equal to 1/2 epsilon naught squared. So if we, so the sum of these two expression is epsilon naught E squared. So this, so it is interesting. One of the strength of the fields for B is much smaller, but the energy is actually equally divided between the electric energy and the magnetic component of the electromagnetic wave. Because they're the same. You get it? This expression here is the same as this expression here. And this one, the second expression, is from the magnetic component of the electromagnetic wave. So this is basically one way for me to say that for describing electromagnetic field for certain calculation, we only care about the electric field. For example, if we have this electromagnetic wave and we want to polarize it, and we will talk about what that really means soon, we only care about the electric field. So let me erase my board. All right, so next we will talk about polarization. Polarization for electromagnetic waves is the direction of the electric field. So in the simulation, the wave is polarized along the axis that is parallel of the vertical axis of this green plane. Okay? But this is a very uniform wave, which is nice to use for teaching pre-meds. But the light, for example, from the sun or from most sources, even like those light bulbs, they are not polarized. They have different polarizations, different wavelengths. Maybe there is a simulation here. There should be simulation here. So this is the lecture notes that I posted this morning. So okay. So this is a simulation of, sorry, let me switch. This is simulation of a polarization. First, if we have, okay. So initially, you can come with unpolarized light. This one has many, basically is a mix of many light. You can scramble lights or light from the sun. And then you can pass this through a polarizer. So polarizer only accept component of the lights that is parallel from the axis, in this case, vertical axis. Okay. So the strength of the lights after it passed a polarizer is I after, oh man, I don't remember the notation that I used. Apologize. Yeah, we can just use A out, maybe. All right, so A after or A out is equal to I in times cosine of phi square. So I'll add square soon. Yeah, phi. Phi is the symbol that I use. Square phi. And again, please make sure you know how to use your calculator. So cosine 0 is equal to 1. Because right now, starting from this point, the angles don't have to be 0 or 90. Could be 31, 32, 33, minus 33. So let's return to the simulation. If the incoming light, so I in has a polarization that parallel from the second polarizer, then all the lights pass through. But when I rotate the polarizer, and then when it reach let's say perpendicular, there is no light that pass through. So that makes sense mathematically. If phi is let's say 90 degree, then cosine 90 degree is 0. But if if you align them, cosine 0 degree cosine minus 80 degree, you square them, is equal to 1. Okay? And there is this nice demo here. Camera. Work. This one is, so I don't know, ASU. So let's say you want to image ASU. This is two polarizer. And this light here is unpolarized light. So when I add polarizer, I lose half of the intensity. And we will do that mathematically, because I know some of you are really good with numbers. And then I have the second polarizer. So this one, right now, I try to do it exactly like this simulations. These two, it has every polarizer has its own polarization axis. So when it's parallel or phi is equal to 0, there is very little light loss. Basically, you still get 1/2. But when the angle, so I'm going to show you the angle. Phi is the angle between these two orange tips. And quickly enough, you can see that you will lose. So at 90 degree, there is no light that pass through the camera. You cannot see anything under this. This is because cosine 90 degree is equal to 0. And this is equal to cosine phi divided by 4 if you want to use gradient. Any question? And the reason why we square it, because the energy is proportional to the square of the electric field. Okay. All right, so we can do a little bit math here. So when you come, so let's say I in is from the sun, which is unpolarized. Then what is this? And then so this is light from the sun. And then you apply polarizer, something like this. This is the axis. So what is phi? So the light from the sun is unpolarized. What is phi? What is the angle? It's unpolarized. So that means it has all possible polarization. It's 2D, but it's actually 3. So phi can be anything, meaning the sum of everything. So for if you come with unpolarized light, then the intensity of the output is equal to, or this symbol here means the average. The symbol here. I don't know, maybe in your high school or your math, you use this symbol. It's the same thing. Or maybe some textbook use different symbol. So this one is basically IN. You cannot average IN, but you can average cosine square phi. So what is the average of cosine square phi? So phi can be from, the cosine phi looks like this. This is phi, this is 0, and this is 2 pi, or 360. Sorry. This is 180 actually. So that's phi. And then phi, cosine phi, or this is cosine phi. So what is the average of cosine square phi? It's okay if you don't know, because it's it requires math, but there is actually a trick. So do you know this from your high school? know that, right? So, and then the average is basically, if we calculate average mathematically, is basically the area under the curve. So if we want to take average of all possible phi, which is from 0 to 2 pi, we just need to calculate the area under the curve. Since sine square and cosine square under the curve, if you add both of them, is equal to 1. And sine square and cosine square, they are symmetric if you shift by 90 degrees. Then the average of sine square is 1/2. The average of cosine square is 1/2. So this one is 1/2. So that's the reason why when we put one polarizer, we lost half of the signal. No matter how I align the polarizer. But after the first polarizer, the light is already polarized. Then the intensity of the output lights is a function of the angle between the polarizers. So what have we learned today? We learned about electromagnetic waves. We learned about the energy per unit volume. We learned about polarization. So exam 3 will be until radiation pressure, which is the lecture on Monday, because we don't have time to go over that. Okay? Any question? All right, I'll see you on Monday.